Hello Year 10, it's Miss Bailey here. In this lesson we're going to be looking at Avogadro's number. So first quantity to have a think about, what would be another way of saying 2 for these socks? So we'd often refer to this as a pair of socks. How about this box of 12 donuts? What other word could we use instead of 12? So that's a dozen. And then our pack of paper that has 500 sheets in it, you may or may not know what word we use for that. And that's called a ream. So a mole is just another way of saying a particular number. So just like a pair meant 2, a dozen meant 12, a ream meant 500, we can consider our moles in the same light. So 1 mole is equal to 6.02 times 10 to the 23. So it's a massive number. And it is this specific number for a reason. So it is because it's the number of atoms in 12 grams of carbon-12. So in 12 grams of carbon-12, there are 6.02 times 10 to the 23 atoms of carbon-12. Could you please pause the video whilst you write that down? So to try and contextualise that number, thinking about how large that number really is. So if we were to take rice grains and fill all the land areas on Earth, it would cover the Earth with a depth of 75 metres. If we were to take marshmallows and cover the US, that would cover it to a depth of 600 miles. If we gave a mole of pennies to every person on Earth, then everyone could spend £1 million a day for 3,000 years. So it's a massive number. So whenever we're talking about a mole of a substance, we're talking about it in terms of their representative particles, and that is the smallest unit of something. So could you please pause the video whilst you define what a representative particle is? So representative particles vary depending on what we're talking about. So it could be an atom for elements which don't exist as molecules. So examples of these are metals such as lithium. So here lithium, when we see it in equations, it's just Li, so therefore just that atom of lithium. So again, pause the video whilst you define that. And then if we have elements in molecules and compounds of different elements bonded together, then our smallest unit becomes a molecule. So an example here is water. So when we talk about a mole of water, we're talking about a mole of the water molecules, not the individual atoms. And this similarly applies for oxygen, nitrogen, the halogens and hydrogen, where these elements are existing as diatomic molecules. When we talk about a mole of oxygen, we're talking about a mole of the O2 molecules. So if you can pause the video whilst you make a note of this definition. And then our final definition here is about our ionic compounds. So ionic compounds have giant structures with lots of ions, but it's the ratio of the ions that are given by the ionic formula, and it's that formula unit that is our representative unit. So there's a typo here, so I'll just cross that out. So that should say sodium chloride. So sodium Na and Cl are chlorine. So what we have here is our ionic compound with our alternating ions, so alternating green chlorine and our blue sodium. So that's our ionic compound in the giant lattice, and still that's just a fragment of the giant lattice that we've symbolised there. But because for every 1 chlorine there is a sodium, we've simplified that down to a formula unit of 1 blue and 1 green. So when we're talking about a mole of sodium chloride, we're talking about a mole of NaCl. So pause the video whilst you write down this third type of representative particle. So question for you, how many representative particles, aka donuts in this example, are there in 2 dozen? So the answer here is 24. So we've got 2 boxes of donuts. Each box contains 12 donuts. 1 box is also equivalent to a dozen. So 1 dozen is 12 donuts. So if we've got 2 dozen, we then have 2 lots of 12, which gives us 24. Okay, so let's have a look now at how we can use Avogadro's number. So just like what we did with the donuts, we can have a look at it in terms of our moles and in terms of our different representative particles. So in this first worked example, we're looking at how many atoms there are in 1 mole of lithium. So thinking about the values that we know our number of moles is 1 mole, and we know that Avogadro's number is 6.02 times 10 to the 23. And what we're after is our number of atoms. So I'm going to call this A. So the way we get our number of atoms is we look at how many moles we have and how many particles are in and how many atoms are in that 1 mole. So our Avogadro's number, in this case, because lithium exists as atoms, our Avogadro's number is in terms of atoms in 1 mole. So in 1 mole, we have 6.02 times 10 to 23 atoms. So we're going to be doing our number of moles times our Avogadro's number. So in substituting that into the equation, we're doing 1 times 6.02 times 10 to the 23. And so that comes out to be 6.02 times 10 to the 23 atoms. Pause the video whilst you have a go at question 1. So in question 1, we have 6 moles. We're dealing with a metal, so again, our Avogadro's number is in terms of atoms. And again, we're after our number of atoms. We're using the same formula. And this time, we're going to be doing 6 times 6.02 times 10 to the 23. And that comes out to be 3.61 times 10 to the 24 atoms. So question 2, we're now looking at a molecule. So water is H2O, carbon dioxide is CO2. So we've been told we've got 2 moles of water, and Avogadro's number is now in terms of molecules. So we need to know how many atoms there are in 1 water molecule. So that 2 there tells us we've got 2 hydrogens, and then we also have 1 oxygen. So H2O is 3 atoms in 1 molecule. So the equation we need here for our number of atoms is going to be our number of moles times our Avogadro's number. But in this case, we also want to times it by 3 because that's the number of atoms for that 1 molecule. So here we're going to be doing 2 times 6.02 times 10 to 23 and times that by 3 to get it into our number of atoms rather than our number of molecules. And so actually this becomes the same as our previous answer, 3.61 times 10 to the 24 atoms. Because whilst we only have 2 moles of molecules, each molecule is made up of 3 atoms, and so actually there are the same number of atoms in each of those cases. pause the video whilst you have a go at question 3. So question 3, we have 0.3 moles. Our Avogadro's number is in molecules. And CO2 also is 3 atoms in that one molecule. We've got 2 oxygens and 1 carbon. And again, we're after our number of atoms. So here we're going to be doing our number of moles times Avogadro's number, and again times 3, because that's our number of atoms in that one molecule. So we're going to be doing 0.3 times 6.02 times 10 to the 23 times by 3, and that comes out to be 5.42 times 10 to the 23 atoms. Coming up with your own counting unit, so instead of a mole, we could talk about different types of counting units depending on what we're counting in. So an example that I have used is pasta, and I weighed out 25 grams of pasta, and there were 22 pieces of pasta in that 25 grams. So if you can't do this at home, use my example. So you can then use this to follow through for the rest of the questions. So instead of kernels, we're talking about pasta pieces, and instead of popcorn, we're talking about pasta. So if you're able to do this with something that you've got at home, so here I'm talking about dried chickpeas. Don't open a tin of chickpeas unnecessarily. Popcorn kernels is something else you might have. Dried lentils, rice, but with rice I would choose a much smaller mass because otherwise you've got a lot there to be counting. So this part of the worksheet is looking at our counting unit system. So as I was saying on the PowerPoint, if you're not able to do this with something yourself at home, then use my system of a pasta counting unit. So there I weighed out 25 grams of dried pasta, and I counted the number of pieces that there were in those 25 grams. And that's going to be equivalent to 1 pasta counting unit. And so what I found was that in 1 pasta counting unit, there was 25 grams of pasta, and that was equal to 22 pieces of pasta. So in this table, I'm going to be looking at the number of pieces, what my pasta counting units are, and then what my mass of that pasta would be. Question 3, we have been asked to calculate the number of pieces in 3 pasta counting units and the number of pieces in 50 grams of pasta, and how we would calculate the mass of 1,000 pieces. And these 3 questions here will set you up nicely for this table. So what I'm going to do is I'm going to work through that pasta example for question 3, 4 and 5, so that you are then able to go on and complete that table. So in 3 pasta counting units, we're going to be having 3 lots of that 1 pasta counting unit, which was 22 pieces. So 3 times 22 gives us 66 pieces. How we would calculate the number of pieces in 50 grams of pasta? Well, here we would look at how many times that 50 grams, how many times 25 grams goes into 50 grams. So 50 divided by 25. And then what we need to do is then times that by the 22 pieces that are in that pasta counting unit. So 50 divided by 25 is telling us how many pasta counting units we have in that 50 grams. And that answer there is 2. So we have 2 pasta counting units in the 50 grams. So we then want to do 2 lots of the 22 to get our number of pieces. and that gives us 44 pieces. And then how we would calculate the mass of 1,000 pieces. So we know that 25 grams is equal to 22 pieces. But if we find out the mass of one piece, so dividing 25 by 22, we can then times that by 1,000 to get our mass of 1,000 pieces. And that comes out to be 1,136 grams. So hopefully you should now be able to complete the table, doing those same kinds of calculations, working it back to our number of pasta counting units to then be able to get our mass or our number of pieces that we have. Thank you all for watching and see you next time.